Hey everybody, Dr. A here, and in this video we're going to be exploring an example dealing with distributed loading. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. Alright, let's get started.
In this example, we're being asked to compute the total equivalent load acting on a beam by two different methods. Part A is using the integral form that we saw in the previous video, and part B is using basic geometry. Okay, so let's go ahead and draw our beam. And this is all given information. So we have this beam and it's subject to a uniform distributed load, kind of like I mentioned in the at the end of the previous video. And this beam is 15 feet long and it has an intensity W as a function of X equaling 2 kips per foot. And I'm just going to be proper. I'm going to go ahead and put some axes on here. That's the W axis. And this is the x-axis, so we see that this left support is the origin, okay? So let's go ahead and take a look at the solution here. So the first thing I want us to notice is this is a uniformly distributed load. Now, why is that? I'm going to say that's because the load intensity is constant over the beam's length. Okay, there's no variability here. It's just throughout the entire length of the beam, the distributed load is constant with an intensity of 2 kips per foot. So that means that every foot of this beam is experiencing 2 kips, okay? And it's not changing. So this is essentially like a constant function, okay? So we can think of this, we're going to say think of this mathematically as a constant function of just 2, okay? 2, and it's got units of kips per foot. All right, so part A says to determine the total equivalent load using the integral form that we just saw. So let's look at that. Part A, we're going to say F equals, and we're going to say integral from 0 to L, W as a function of X, dx. All right, so in this case, W as a function of X is just 2 kips per foot. I'm going to keep my units in there just to be proper. So I'm going to take the integral from 0 to 15 feet of 2 kips per foot. Okay. And then that's dx. Be mathematically proper there. So when you take this integral, again, it's an integral of a constant. That's it. So we would say 2x, or you can, if you want to, you could keep the 2 kips per foot times x, right? That's it, just 2x evaluated from 0 to 15 feet, okay? And so let's substitute that in. Remember, it's upper limit minus lower limit, so we're going to say 2 kips per foot times 15 feet minus 0 feet, right? Upper limit minus lower limit. So we get F equals 30 kips. And I kept the units there on purpose to really emphasize that if you look at this, the feet in the 15 feet cancels in the per foot when we have 2 kips per foot. So then we're just left with units of kips. Now, the next question is, what do we do about the sign convention? Well, here's how I like to handle it, and different people may handle this differently. So if you find another resource that explains it a little differently, that just gives you some varieties of ways to approach these kind of problems. So here's the way I like to do it. So my origin is here, and my w-axis is positive pointing up. And if I have this uniform load here, right here, again, this is like a constant function, right? This is like you don't have to draw this necessarily if you don't want to, but that's kind of like if you have like y and x, and you have a constant function of 2 right here. That's mathematically essentially what you have, a constant function of positive 2. Okay, so so that's how I think of it. Now, notice that this load is pointing down. Okay, this load is pointing down. So what I like to do is I like to take this as positive because it's like up here in the positive w axis. So I take this as a positive 2 when I'm looking at my integral. But then at the end of it all, I put a downward arrow, because even though I'm taking this as a positive constant, it still physically represents a distributed load acting on a member, and that load is pointed downwards, right? That's a downward acting distributed load. So I will go ahead and put a downward arrow here. Now, some people, they'll put a negative sign in attached to the 2 here, and then when they evaluate that integral, there's a negative sign built in to their final values, and then they take that to mean negative is pointing down. But again, I prefer just to keep it in the positive form and then just look at it physically. Okay, it's pointing down, so I put a downward arrow here. So that's the integral form, okay? Now, part B said do this same thing, but using the geometric form. So what do you think I mean by that? When I say the geometric, using geometric methodology, what I mean by that is just compute the area under the load distribution. Well, what is the area beneath the load distribution? We'll look at it. It's just a rectangle, right? It's a rectangular area. For a uniform load distribution, it's a rectangular area. So let's make a note of that, right? So for a uniform load distribution, this is a rectangular area. So all we have to do here is say F equals 2 kips per foot. Okay, what do you think that represents? Well, the 2 kips per foot represents the height, okay? The height is the 2 kips per foot, and then the length is the 15 feet. So you have like height times length gives you the area of a rectangle. So we say times 15 feet, and of course, this is 30 kips, and it's still pointing down. So I'll make a little note here. This 2 kips per foot represents the height of the rectangle, and then the 15 feet represents the length of the rectangle. So you got, length times height or length times width, however you want to think of it, and that's 30 kips going down. So that's it. That's it for this simple example.